All right, so this is section 3.5, graphs of rational functions. We'll start with the definition of a rational function. Let P and Q be polynomial functions with Q of x not equal to 0. Then the function f of x equals P of x over Q of x is a rational function. The domain is all real numbers x such that Q of x cannot be 0, and that's because you have a fraction, so you cannot have a denominator 0. Some notation. As x approaches a negative, and notice the negative is in the place where the exponent goes, means x approaches a from the left, and a is some number, some constant. As x approaches a from the positive, or a with a little plus where the exponent is supposed to be, means x approaches a from the right. X approaches negative infinity means x is a very large negative, and approaches positive infinity means x is a very large positive number. All right. Letter B, use a graphing utility to graph f of x equals 1 over x and answer the following. So, we'll graph it once we're in class. For now, let us analyze it. So we'll use some values of x to analyze what happens. All right, so number 1 says, as x approaches positive infinity, f of x approaches blank. So what does f of x approach? Again, remember f of x is a value of y. For some value of x. All right, so let's think about some values of x. So, and also we want to know f of x equals 1 over x is the reciprocal function. That means whatever x I input, I get back the reciprocal for y. Okay? All right, that'll be helpful to know. So f of x, so as x approaches positive infinity, so if we think of numbers getting larger, like x equals 100, then 1,000,000, then 1,000,000,000, f of x approaches 1 over 100, right? For x equals 100, y will be 1 over 100. For x equals a million or 1,000, y will be 1 over 1,000, which is smaller. As x approaches a million, f of x will be 1 over a million, yeah, which is 0.00001, 5 zeros and a 1. And as x gets bigger, y just gets smaller, closer to 0. So f of x then approaches 0. All right. Number 2, as x approaches negative infinity, f of x approaches what? Well, it's the same thing, just on the negative side. So you're going to, let's say, substitute for x negative 100, negative 1,000,000, negative 1,000,000,000, and you're just getting closer to 0 just from the negative side. Okay? That means if you consider points, on the first one, you're getting closer to 0 from above the x-axis. And as x goes to negative infinity, you're going closer to 0, but from below the x-axis. Okay? All right, number 3, as x approaches 0 from the left, or from the negative side, what does f of x approaches what? Okay? So, let's consider some numbers. Let's start at x equals a negative 1 from the left. So x equals negative 1 gives us f of x equals negative 1. X equals negative 0.1 gives us f of x equals 0.1, which is 1/10. F of x equals negative 10. As x, if x is negative 100, then 100th, then f of x is the reciprocal negative 100. And if x is negative 1,000,000th, then f of x is negative 1,000,000. So you'll notice your y is getting very large but negative because all these numbers are negative. And so you're just getting very large negative, which means negative infinity. And number 4, as x approaches 0 from the right, same thing is happening except the numbers are positive. So you're getting away from the x-axis as you get closer to x equals 0. But on the positive side, your numbers are getting away from the x-axis, or your points are getting away from the x-axis just on the positive side, or towards positive infinity. And you can plug in some numbers like 1/10, x equals 1/10, so f of x would be 10. X equals 100th, f of x would be 100. X equals 1,000,000th, which is really close to the y-axis, and your y value would be 1,000,000. Right? So you're approaching positive infinity as x approaches 0 from the right. Okay. If you think about the curve, by the way, as x approaches 0 from the left, f of x approaches negative infinity. It means your graph is dropping as it approaches the y-axis. And on the right-hand side, as x approaches 0 from the right, your graph is increasing. Going up as x approaches the y-axis. Okay. let's go on to the next part, which is called part 3, but it's really the second part. Graphing rational functions. So remember f of x equals p of x over q of x. And then remember also each of those is a polynomial, and what does a polynomial look like? So p of x we're going to say is a sub n x to the nth plus a sub n minus 1x to the n minus 1 plus and so on, all the way down to plus a sub 1x plus a sub 0. And q of x we're going to say is b sub m x to the mth plus b sub m minus 1 x to the m minus 1 power plus and so on plus b sub 1 x plus b sub 0. Notice that the leading coefficient of the top is a sub n, the leading coefficient of the bottom is b sub m, and the exponent exponent of the leading term is n on top and m on bottom. All right, so letter A, horizontal and slant asymptotes. So first, number 1, n behavior refers to the graph as x goes to positive or negative infinity. Does not mean that the graph actually goes to both, but to either one that it goes to. That's what you're looking at when you say n behavior. Number 2, if n is less than m, which means the exponent, the leading exponent on top is less than the leading exponent on bottom, or the biggest exponent on top is smaller than the biggest exponent on bottom. The n behavior asymptote is a horizontal asymptote y equals 0. The line y equals 0, that's the horizontal asymptote, which happened, by the way, on f of x equals 1 over x. Number 3, if n equals m, then the n behavior asymptote is the horizontal asymptote y equals a sub n over b sub m. So notice you construct y equals the number constructed by a sub n over b sub n, which is the leading coefficient. Okay, and we'll come back and we'll see why. If n is greater than m, then the n behavior is the quotient y equals d of x, where p of x over q of x equals q of x times d of x plus r of x. What that means is that you actually carry out the division of the polynomials, and you'll get what is called the quotient d of x, and then you might get a remainder r of x, okay? And so you use d of x as what your graph looks like at the ends, the n behavior. Okay, now why, if n is less than m, is the n behavior asymptote y equals 0? Well, if you consider that the top exponent is smaller than the bottom, like for example, let's say any number, and we'll just look at the difference of 1. Right, it can be worse, but it could be a difference of 1. So like x to the 5th over x to the 6th, let's say something like that. So if you notice, that will reduce to 1 over x, and so that means that it's really following the n behavior of 1 over x. Maybe not exactly the same, but very similarly, they'll go to the same line y equals 0. All right, if n equals m, well, if you think of x to the 3rd over x to the 3rd, they'll just cancel out. X to the 4th over x to the 3rd, they'll just cancel out, right? The only thing that'll make a difference is the leading coefficients. So if you have 2x to the 3rd over 3x to the 3rd, the x to the 3rds cancel, but you still keep the 2/3. And that's why your horizontal asymptote is a sub n over b sub m. All right, and for number 4, the same thing. So when you carry out the division, whatever answer you get, like let's say you divide and you get as your quotient 2x plus 1. So that means that in the end, as the x values get very large, your graph just starts following that particular graph, y equals 2x plus 1. Okay. Number B, vertical asymptotes. So how do we find these? These occur at real zeros of the denominator, provided they are not also real zeros of the numerator of equal or greater multiplicity. And what that means is if you have the same factor on top and bottom, that you don't count that one as a vertical asymptote, or that one doesn't come into that consideration. Okay, and we'll see what happens to those. Letter C, x-intercepts are zeros of the numerator that are not also zeros of the denominator. Notice the same situation as on the previous statement, that if you have the same factor top and bottom, those don't count. Number D, y-intercepts are points where you plug in x equals 0, so f of 0. And then letter E, to find where f crosses the horizontal or slant asymptotes, if at all, then you set f of x equals that asymptote. So for example, if you have one where the asymptote is y equals 0, then you would set f of x equals 0, whatever f of x is. So f of x could be what we have here in the example, let's look at the example. All right, so example, determine the point of any where the graph crosses the horizontal asymptote for f of x equals x minus 2 over x squared minus x minus 6. So first we find the asymptote. So you'll notice the power on top is less than the power on bottom, which is the n is less than m part, and the end behavior is y equals 0. Okay, so our horizontal asymptote is y equals 0. So then we said x minus 2 over x squared minus x minus 6 equal to 0. And then we're just going to solve that equation. Okay, so to do that, you know what, let me factor x squared minus x minus 6. So that's x plus 2 times x minus 3. It's just to make sure that the top and bottom don't have common factors. So they don't. So if I multiply times x plus 2 times x minus 3 on both sides, then on the right hand side the 0 times that is just 0, and on the left hand side it cancels with the denominator and I get x minus 2 equals 0, so I get x equals 2. So I have the value of x. To find the value of y, I just find f of 2. So f of 2 is 2 minus 2 over 2 squared minus 2 minus 6. You notice the top is 0 and the bottom is non-zero, so you'll get 0 over something which will be 0. Okay, so the value of y is 0. So the point where this graph crosses its asymptote, y equals 0, will be the point 2, 0. Alright, I'm going to say that's the end of part 1, and we'll continue with the next page on the next part, which will be part 2.